Now we're going to start part 2 of Lecture 7, Radar, Clutter, and Chaff in the Introduction to Radar Systems course. Now let's move on to sea clutter. Sea clutter is very different than ground clutter. And there are a couple of sort of bumper stickers, points I'd say up front. The first is it's a lot less intense. It's about 100 times less intense than ground backscatter. That's the good news. There's always bad news. The bad news is that the ocean moves. So you've got, and the ocean moves with the wind. So you're going to have a motion of the backscatter because a lot of what you're reflecting off of are waves. And the waves will move at 10, 15, 20 knots, 30 knots, and of course at very high sea levels, we call them sea states. That'll be a lot more. You're going to have a Doppler, significant Doppler. And particularly if you're in a sea environment, there's a good chance you're going to be on a ship. And so you're going to have the Doppler of the ship thrown into play. Now, what are the other variables? Well, we've got the wind and the weather, as I said. And how we characterize that is by sea state, and I'll go over that in a minute. We also have the frequency and the polarization. And just to take a look at that, and there are all kinds of graphs like this. This is data of the mean cross-section per unit area. Again, this is a cross-section per unit area because you're looking down at an area on the surface, albeit the sea, as a function of the grazing angle that you're looking down at. And it's measurements that were taken by the Naval Research Laboratory. And these are smooth curves that are hand-drawn through the different data. The wind speed's 10 to 20 knots. This varies somewhat with the wind speed. And it's taken for two polarizations, horizontal and vertical. And what this clearly says to you, if you don't want, if you're operating at grazing angles below 30 degrees, the clutter will be a lot lower if I have on my radar a horizontal polarization. So that's one thing you might see. It's like a message the clutter can have for you. And the clutter can depend on the resolution of the radar. It will depend, and the cross-range resolution. You can clearly see that the clutter cross-section depends on the grazing angle. If you're looking at very high grazing angles, the clutter is extremely strong. There's a factor of 40 dB between the 0 grazing angle and 90 degree grazing angle when you're looking straight down. And there's just a lot of variables. Now let's just mention, so if you're not familiar with sea state, the World Meteorological Organization has developed a table that's world recognized as how rough the sea is. And radars, ships are specified that they like naval ships. The radar ship shall do its mission in sea state 5. You know, if it's sea state 6, you want to batten down the hatches and try to get to sea state 5 usually. And you can see these sea states are characterized by a range of wave height and a range of wind velocities, and then a descriptive term. Okay, so that when radars are built, typically in a naval environment, they're built to operate up through sea state 5. In civilian radars, they may be less. Okay. Now, there's one clutter attribute that's unique to the sea that I want to mention about, and that is what is phenomenologically called sea spikes. And this is the best way to characterize these phenomenologically is to show you some data. Researchers Lewis and Olin at Naval Research Laboratory collected this data. It's at a grazing angle of 1.5 degrees, horizontal polarization, and here's the radar cross-section going from 0 to 10 meters squared. So you can see it's down low most of the time, but then for periods of a second or two or three, The cross-section that you see from the sea, no pun intended, goes up to near a little bit below 10 meters squared, quite significant. Okay? So at low grazing angles, sharp sea clutter peaks known as sea spikes appear. And these sea spikes can cause excessive false detections in the radar. And they can cause because if you get a detection, you send out, particularly if you have a phased array radar that can go boom, 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 boom with pulses to see if there's a target. You want to measure its velocity very quickly to see if it's coming at a ship, a destroyer, or a cruiser very quickly. You send out those confirming pulses, and you'll see confirming pulses but then they go away. And so it's an issue that that exists and needs to be handled because they actually exist. Now, the other thing I'd like to say is just phenomenologically there's a lot of discussion about what these actually are. And my best guess is that if you look out at the sea and you have a fairly robust sea, that you have waves, and the waves go up in a curved area, the curved area. And what you're seeing is the collective, coherent reflection of a wave or two. Then a good portion of the length of a pulse maybe, enough so that for a little piece of time, you get a good solid backscatter, and then things interfere with one another. But it's obviously a physical phenomena that's out there in the ocean that naval radars need to deal with and do deal with. Okay, now it's time to start the next section. We're going to start first with rain. Now, rain is a little bit different than sea clutter or land clutter in that it's a volumetric clutter. Now, rain both attenuates and reflects radar signals. And just imagine a big rain cloud out there. The electromagnetic energy goes through the rain cloud and it scatters, so there's going to be a little less energy after you go through the rain cloud. So that's a loss that occurs in the radar equation. But it also reflects energy back to the radar. Problems occur with rain. They lessen dramatically with longer wavelengths, lower frequencies. And that's because, if you remember back to the cross-section lectures, the cross-section of rain depends on the size of the raindrops. And when the wavelengths of the radiation of the radar get very small, and they get near raindrop size or they approach raindrop size, things get large and resonant. And when the wavelengths of the radar are much larger, then rain's backscatter drops down significantly. What this means is that rain is much less of an issue at L-band, 23 centimeter wavelength, than at X-band, 3 centimeter wavelength. And rain is diffuse clutter. It isn't, it's diffuse wind-blown clutter, I call it. It travels horizontally with the wind, and it has a mean Doppler velocity, and that Doppler velocity has a spread. This cartoon shows a beam, electromagnetic wave going out and refracting inside the raindrop, reflecting back, and then reflecting out of it. So what you're seeing is the reflection inside the raindrop. Okay? Now here's what rain looks like on a PPI, a plane position indicator display. And this is a radar located in Atlantic City, New Jersey, at the FAA's test centers. It's an S-band radar, and the radar has a sensitivity to see a 1 square meter target at 60 nautical miles. And we see here the buildings on Atlantic City. It's actually located in Absecon, New Jersey, very near Atlantic City. And this little line is actually a lot of distinct detections of the towers of electrical lines high power electrical lines. Okay. Now this is on a clear day, no rain. There's some ground clutter here. South Jersey is relatively flat. Okay. Now over here we see a PPI of the same geographic location when very heavy rain. This was taken in August of 1975. See, this is what a rain cloud would look like, and it would move across slowly at whatever the prevailing winds are taking the rain through the region. In this case, we'll see later in Lecture 8 that this was extremely heavy rain. Okay. Now, when we look at the backscatter of rain, we characterize it with a backscatter per unit volume, because as you can imagine, since it's a volumetric clutter, the larger the volume, the more more rain you're going to see. And so for a drizzle, which characterizes, it's about 1/4 millimeter an hour, at S-band, minus 102 dB meters squared per meter cubed of volume. And so these coefficients, which are roughly good to about 2 or 3 dB, are good numbers to use. And then you can see that rain varies at S-band. It varies from a light drizzle to heavy rain, 30 dB. Okay. Now, the reflectivity across wavelength, because it's a relatively simple to calculate, the rain reflectivity varies as the frequency to the 4th power, or 1 over the lambda to the 4th power. And that's how the rain clutter is an issue at S-band, at these air traffic control radar frequencies, but a very significant one at X-band and even more. You can see that it's over 100 times much more intense a light drizzle is at 35 gigahertz than at X-band. And at heavy rain, it's 2 orders of magnitude. So you can easily see this 2 orders of magnitude from going from 9 to 35 gigahertz. Yeah, more intense at K-band, 35 gigahertz. Okay, now what does the Doppler spectrum look like? If you take an S-band air traffic control radar, and you just point it in one direction, you don't have it rotating at that 12 RPM, but point it in one direction, and look at an individual range cell, and you look at the Doppler spectrum that you see. When there's nothing there, you just see down here at this is at a relative scale of dB, but a dB, but a relative, it is an absolute measurement of cross-section. But you see the noise level is down around 75. Okay? But when it's raining, as it was when the azimuth was at 90 degrees on this particular day, you can see that the rain is not down at 75, but it's more up near 50, minus 50 dB. Okay, and likewise, when you turn just a little bit over 90 degrees, well, let's see, 320, 40, and 90, 130 degrees, we see the Doppler moved in this direction, and then we move another 10 degrees over, and we see the Doppler distribution is even different. So one of the things that you have here, and you notice rain is, first of all, it isn't Gaussian. The mean velocity varies as the storm moves by the radar. And this was an example of rain that was about 20 millimeters an hour. The winds were 30 knots on the ground and 50 knots at 6,000 feet. Okay, and there was a spread of about 6 knots to the Doppler velocity. Okay, that'd be full width at half max. At 3 dB down, that'd be the width 3 dB down. This was just a curve fit by hand. And so you can see it's bimodal. And another thing is that just think of a rain cloud moving towards towards you. If it's moving towards you, it's going to have a strong Doppler. If the rain cloud is moving tangentially, the average Doppler of the rain will be 0, much like at this 90-degree case. And if it's moving towards you, pretty much towards you, away from you, 330 degrees, you see this kind of an effect. So the rain can move all over the Doppler space. And notice that here is 0 Doppler, and here is plus 60 knots, and here is minus 60 knots. Now you can see here that the Doppler, because of the pulse repetition rate of the radar, the ability of this radar to measure unambiguously the Doppler is impeded. This radar can only see plus or minus 60 knots, and we'll go into the details of that. There's blind speeds and also ambiguous range issues in the next. But notice that the downside of the Doppler here, when its velocity is negative, minus 60 knots, shows up here as a positive Doppler. So one of the things that you'll notice is that there's a folding over effect that occurs in many radars, and this is an example of it. I'll just note it in passing, and we'll examine it in a lot more detail later. Okay, now on to chaff. I mentioned earlier that chaff is aluminum foil. It's large numbers of dipoles that can be metallic or lightweight substances that are metallic coated. You want high reflectivity per pound, and the optimum length is a half wavelength, the dipole. You get the biggest cross section per pound. And what you do is you eject these, lots of them, and they move out with the wind. And the uses of chaff, first you can mask a giant area that can shield aircraft or missiles in or near a cloud. You can put up deception chaff, it's called, a little puff of chaff to emulate a missile or an aircraft and have a tracking radar. It would cause false detections and take a tracking radar off track of the actual aircraft, and it would track the chaff. And packets of chaff can divert that radar tracker from the target, as I just mentioned. Okay. Now, what's the cross-section? And these are numbers that are taken from open literature. These were published also in Fred Nathanson's classic book. Resident metallic dipoles have a cross-section of 0.18 times lambda squared in meters squared. So if you take a dipole and just take its wavelength, square it, its wavelength in meters squared, that'll give you the cross-section of 1. But you want to put out an awful lot. And the bandwidth typically is about 10 or 15%. And if you take lightweight aluminum thin dipoles, they tend to drop at from a half to 3 meters per second. It takes quite a while for them to drop. For aluminum foil dipoles, which are 1/1000th of an inch long, 1/1000th of an inch thick, 100 by 100th of an inch, and a half a wavelength long, here's one of those rules of thumb that engineers have. The cross-section is 3,000 times the weight in pounds divided by the frequency in gigahertz. And that's the total cross-section of the chaff. So you could say if you have 400 pounds of chaff and it's an S-band, you can generate 250,000 meters squared in cross-section, and you can sprinkle that out. So if you put in each range cell 1,000 meters squared of cross-section, you can wipe out 256 range azimuth cells with 400 pounds of chaff, or at least raise the cross. It appears as though there's 1,000 meters squared cross-section there, which one has to deal with. Now, what do these chaff-dispensing systems look like? This particular one it's a relatively old one. Again, it's taken from the open literature. It was republished in several places, and one of them is in Fred Nathanson's book. and it's been redrawn. The chaff is put out sometimes in boxes and sometimes in rolls. These look like toilet tissue, literally, but they're little. The dipoles unroll, and a little motor unrolls this roll of chaff, and it's set to preset lengths. And to disperse it, a rather unique method is used this is a pod that would be on the wing of a plane, or the underbelly of a plane, typically a wing though, and air would go ramming in to at say 600 miles an hour, 500 miles an hour, and it would go down a tube, and then just as the chaff came off the roller, the 600 mile an hour jet of air would impinge on that chaff just as it exits, and with a great flare of turbulence, and so it would just bloom the chaff all over the place, give it all sorts of, and the chaff would just bloom all over the place. Okay, now I'm going to show you what chaff looks like, and here we see a movie. It's speeded up many times. This was a chaff drop done at Atlantic City. You can see very quickly, it's about 35 times real time. Each one of these clicks, and the clicker over on the right is 4.7 seconds. And you can see the chaff is blown by the wind, and it's filling up a big chunk of area. And in this case, it was about 400 pounds of chaff dropped as fast as the airplane could drop it. Let's look at it one more time. And this is the airplane going out, dropping the chaff behind it, taking a dog leg to the right, and then it finished dropping it, went on its business, and then you can see as the chaff drops, the wind is just blowing it out over the area with cross sections that were 1,000 times greater than the ambient noise level of the radar. Okay. Now let's go on to birds and insects. That I call it the funny part of clutter. Okay, first, there are lots of birds. We all know there are lots of birds. People all over the United States go out and look for very single, rare birds. And we know there are thousands upon tens of thousands of species of birds. And one of the things they do is, and I have a couple of view graphs here to point out that they, even if you look at a simple single bird, they really travel an awful lot. So they're up in the air a lot. And here we have the gadwall, and where it breeds in winters, they just fly back and forth every spring and every summer. And here the northern flicker, it breeds up north, and then they come down and they winter down in the Gulf. And each different, the Virginia reel breeds up here and then comes down to winter along the Gulf. And during the breeding season in the Gulf Coast, sea and wading bird colonies exist with up to 60,000 birds, 10,000 are common in a colony. And these birds each weigh a kilogram, and they have a wing spread from 3/4 to several meters. In other words, they're pretty good-sized physical entities. Here's another set of birds. One set of blackbirds, 63 blackbird roosts were found in the Mississippi Valley, each having 1 million birds in them. Okay, and these birds go out 30 miles every day for feeding. So birds are all over the place. A couple of other bits of information I point out. In the fall, millions of birds leave New England, and they go out over the Atlantic. They go up to 17,000 feet, and they fly, and some of them land in Cuba, and others go down, and they land in northern South America. And this has been validated by radar ornithologists who used tracking radars up and down the coast to follow that incredible journey. Just incredible. Most European birds migrate to Africa over a 7 or 8 week period in the fall, and they come back in the spring. So the Mediterranean, what we think of as a bird clutter-free region, because it's hundreds of miles by 1,000 miles. Now, significant portion of the time, there are incredible numbers of birds migrating. And the number of birds per square mile, the density of migrating birds, it varies from 1 per square mile up to 1,000 per square mile. So if you've got a radar that sees, say, 100 miles by 100 miles, 3,000 square miles, and you multiply that times 100, that's the number of birds in your coverage. Well, the next thing you can say is, well, bird cross-sections are real small. No. A lot of the time, the bird cross-sections are up in the region such that if there'll be enough of them in the cell, the radar cell, that you'll see them quite readily. Because you have so many birds in the coverage, enough of them have a cross-section that's big enough to see. And they also have a radial velocity. They just go in with the wind. They're very efficient entities. So even though they're very small, their echoes are small, they're relatively small individually, the densities are so great that birds can often overload radars with false targets. And since the birds move relatively low velocities, their speed, if measured, can be used to threshold out the low velocity birds. But they still can be a problem. Excuse me. Now here we see output from an airport surveillance radar in Dallas, Texas during a time of particularly strong bird migration. And these radar uncorrelated returns that you see moving from south to north are all, click it again, are all birds detections that are leaking out of the system. Now, luckily, we've got beacons on aircraft. You can see that this color, and you can see that they're from aircraft. And what are displayed here are the last 10 scans of the radar. So a clear aircraft would be a little worm that's that color. It'd have a radar and a beacon returns. But you can see a lot of birds, and this is one of the worst days in several years. Not several years, but the worst day or two of a year down in Dallas. It's like that when the birds are migrating. So birds are a significant issue for our radars. So let's just recapitulate very quickly about birds. Birds are actually moving point targets, and their velocities are usually less than 60 knots. They have a mean cross-section that's small, but a fraction of the birds, their cross-section can fluctuate up to high enough aircraft-like levels, and their cross-sections are resonant at S and L band. There are lots of birds per square mile, from 10 to 1,000, and for many radars, particularly radars that are looking at targets that have small cross-sections, they can be a significant false target problem. And now on to insects, as if birds weren't enough of a problem. Bats are also a problem, but I won't get into that. They'd be down in Texas. There are lots of caves where they just come swarming out. Anyway, the cross-section in meters squared of different individual insects can be characterized as their cross-section as a function of mass. And here what we're dealing with are swarms of insects. They can clutter the display and prevent the detection of desired targets if they're swarming in great enough densities. Their densities can be an order of magnitude greater than that of birds. They generally drift with the wind, and you can a good model of them as you look at their size, is a spherical drop of water, about the same size. An insect broadside are a 10 to a 1,000 times that when viewed from end. So now let's summarize all this stuff about clutter. Before we get into the next lecture, we're going to say how we deal with it. The number of different types of radar clutter returns we've been talking about. Ground clutter, sea clutter, rain clutter, and birds we've looked at in detail, and a little bit of insects. These environmental and phenomena, and the man-made ones too, produce a variety of both diffuse and discrete moving and stationary false targets. And you've got to learn to deal with them if you're building radars. And there are a lot of signal and data processing techniques that can be used to beat these effects down so that we can effectively make radars work. And those techniques will be the subject, most of those techniques